Hello and welcome to our next module on BCH codes. Let's start with a brief outline of today's talk. We would start with refreshing our memories regarding the generator polynomial for BCH code, and then we would look at how BCH codes can be effectively used to detect and correct multiple errors, because that is what they are famous for. And finally, we would talk about efficient decoding of BCH code. Let's do a quick recap as to what we have done already. We have introduced the notion of the primitive polynomial and then creating an extension field. Then we went on to discuss what do we mean by minimal polynomials, and then how do we arrive at the generator polynomial for BCH codes. So, very quickly, BCH codes are a subclass of cyclic codes, which are themselves a subclass of the linear block codes. So, all the theory we have developed for linear block codes and cyclic codes are applicable for BCH codes. At the same time, we can have more efficient techniques specifically geared towards cyclic and BCH codes. So, please remember the key difference between what we have learned so far and the BCH codes. In BCH codes, we start from the other end. We decide how many errors we wish to correct, and then we design the particular BCH code for that number of errors being corrected. So, T, which represents the number of errors we wish to decode, that coupled with N, the block length, are the starting points for BCH codes. As we mentioned before, BCH forms a subclass of cyclic codes. Now, in order to do that and also to develop further theory for decoding, we must recall what we meant by a primitive element. A primitive element of a Galois field GFQ is an element alpha such that every field element except 0 can be expressed as a power of alpha. Then we went on to define what is a primitive polynomial. A primitive polynomial p of x over GFQ is a prime polynomial. Prime, if you remember, means you cannot factorize and it is also monic. So, it is a prime polynomial over GFQ with the property that in the extension field constructed modulo p of x, the field elements represented by x is a primitive element. So, you can construct the entire field using powers of x. Now, the good news is primitive polynomials of every degree exist over every Galois field, and primitive polynomial can be used to construct an extension field. Now, why were we doing all of that? That is because we wish to factorize x is for n minus 1, where n here is q minus 1. So, what we have already looked at is if beta 1, beta 2, etc. are the non-zero elements of GFQ, then you can write x is for q minus 1 minus 1 as simply the linear factors of x minus beta I. Then we introduce the notion of primitive block length n equal to q raised by m minus 1, where m is some integer and GFQ is the field over which we are working. So, that is the primitive block length for the code over GFQ. A cyclic code over GFQ of primitive block length is called the primitive cyclic code, and we are doing all of this so as to factorize our x raised by n minus 1. So, we have this x raised by q raised by m minus 1, this is the primitive block length, is nothing but the linear factors x minus beta j. So, we have done all of this earlier, and we have found out that each of the polynomials f I x can be represented in GFQM as a product of some linear terms, and each bi is a 0 of exactly one of the fi's. So, please note that this left hand side is written as factors, and some of them correspond to the minimal polynomial, right. So, if you want to look at it a little bit more carefully, we have x raised by q m minus 1 minus 1. So, this is very conveniently my n. So, we are still looking at x n minus 1 factorization, because we are in the domain of cyclic codes. So, this can easily be written as a product x minus beta 1, x minus beta 2 and so on and so forth, right. Now, what is interesting is sum of them. When you multiply together, you get, so you can have sum of them. So, this is the minimal polynomial. Of these. So, there are several beta i's which corresponds to the same minimal polynomial, and how to choose them we will discuss in the subsequent slides. Now, the smallest degree polynomial with coefficients in the base field GFQ that has a 0 in the extension field, we are looking at the slides again. The smallest degree polynomial with coefficients in the base field that has a 0 in the extension field GFQ is called the minimal polynomial of beta I. Now, we have talked about primitive BCH codes with block length q raised by m minus 1 because it is very easily factorizable, and it is the factor that we are going to deal with. And we went on to define g of x as a factor of x raised by n minus 1, and we can take g of x as an LCM of certain number of minimal polynomials. Please note, each of the minimal polynomials f1x, f2x, fnx, fpx corresponds to a 0 of g of x in the extension field. So, how do we get a g of x for a BCH code? Well, we first set the primitive block length n equal to q raised by m minus 1, that is the starting point. Choose a prime polynomial of degree m and construct GFQM. So, you construct the extension field and then find the minimal polynomial of alpha, alpha squared, alpha cubed and so on and so forth, and finally, you find out g of x as the LCM of f1x, f2x, f2, f2tx. And we did a theory in the last class why 2t is required, so that you can have enough number of equations to exactly correct the required number of errors. Please note that the design distance is t. So, the g of x so designed will guarantee you that it will correct at least t errors. It can be over designed, it can end up correcting more than, but this minimum number of errors we can always correct. We will look at some examples, and therefore, t is called the designed. So, d equal to 2t plus 1 is called the design distance of this BCH code. Now, we should note that once we fix n and t, we can determine the generator polynomial for the BCH code, because k will automatically get determined. The degree of the generator polynomial is n minus k. So, once we know n and once we know the degree of g of x, we must get our hand on k. So, for BCH codes we do not have a control on the information length k. Okay. So, once we get g of x, that will determine the k. So, let us start with some examples. Now, consider a primitive polynomial pz is equal to z raised to power 4 plus z plus 1 over gf2, and we wish to construct gf16 modulo p of z. Now, please note, if you go back to the drawing board, we have p of z equal to z raised to power 4 plus z plus 1. Now, we will perform operation modulo p of z. So, all the polynomials, when we take modulo p of z, which will have some coefficient z cube plus some coefficient z square plus some coefficient z plus coefficient. So, please note that since we are taking modulo p of z, any remaining polynomial after taking modulo p of z can have the highest degree 3. So, we have here a 0 or a 1, 0 or a 1, 0 or a 1 and 0 or a 1 coefficients. So, you have 2 raised to power 4 is equal to 16 unique polynomials, and these will represent your 16 elements over GF 2 raised to power 4. But the only way we would be able to construct this is going with modulo p of z, because p of z is the primitive polynomial. Okay. So, let us complete this exercise. So, we go back to our slides, and if we write down the powers of alpha or a, then alpha is equal to z, alpha squared is equal to z squared, alpha cubed is equal to z cubed, and alpha 4 is z raised to power 4, but it has to be taken modulo p z, which is z raised to power 4 plus z plus 1. So, the moment you divide z raised to power 4 by z raised to power 4 plus z plus 1, you end up having z plus 1, and so on and so forth. You can continue and you can construct these 16 non-zero elements of GF 16. Now, if you take alpha, alpha squared, alpha 4, right, and take the elements and you multiply x minus z into x minus z square into x minus z minus 1 and so on and so forth, which are the conjugates, you end up with the minimal polynomials. So, for example, let us take this example a little forward. So, we go back to the drawing board. So, you have alpha corresponding to z, and you will realize that I have written minimal polynomial x raised to the power 4 plus x plus 1. Similarly, alpha square is z squared, because we are taking p z is equal to z raised to the power 4 plus z plus 1, and again it has the same minimal polynomial. Why? Because they are conjugates. But why should we stop here? We look at alpha raised to the power 4, and when you take it modulo p of z, you end up with z plus 1 again, and then you go back and you look at alpha 8, and alpha 8 is z squared plus 1, same. But the moment you go alpha 16, it reverts back. So, these are the 4 elements. Now, if you want to look at it, your f I x is nothing but x minus z into x minus z squared into x minus z minus 1 into x minus z square minus 1. Please note what we have done. We have taken the first element, second element, third element, fourth element, and we stop here because going beyond we repeat back. Now, if you multiply this out, magically all the z's will cancel out, and you will left with x raised to the power 4 plus x plus 1, which is your minimal polynomial. And similar exercises can be done for alpha cubed, alpha 6, and so on and so forth, and so on and so forth, till you discover all the minimal polynomials. So, it takes a. So, the minimal polynomial will have coefficients in the base field, that is how its definition comes, and we had shown it in a theorem in the previous class. Therefore, Z is an element of the extension field, but base field is GF2, so the coefficients can be 0 or 1. So, therefore, it is a beauty of maths that it will cancel out, and you can show that the minimal polynomial will ultimately have coefficients in the base field. Yes.
Is there a way to write minimal polynomial looking directly at PX?
Question that is asked is, can we write the minimal polynomial directly looking at PZ? The answer is no. There is a standard way to solve for minimal polynomials. You first create the extension field as you have done in the table we showed earlier, and then from the table you have these elements. Now, we also proved last time that certain powers of alpha, when you have linear factors, then you will end up having the products leading to the minimal polynomial. So, this is basically the. So, if you want to continue this logic forward, you know that x raised by n minus 1 is nothing but x minus alpha, x minus alpha squared, x minus alpha cubed, so and so forth, right, till all the elements are there, and that is the factorization. Eyes closed, you can just continue doing this. But the interesting part is, if you take some of them and multiply, you get f1x. If you take some other ones here and multiply them, you get f2x, and so and so forth, and they are still equal to x raised by n minus 1. So, in fact, we are factorizing the left hand side elegantly using all the coefficients from the base field. Okay. So, we continue with our example. So, we go back to our slide and we have suddenly a nice table of GF16 with consecutive minimal polynomials, and a little bit of observation says that look at alpha cubed, right. The minimal polynomial for alpha cubed is the same as alpha raised to power 6, is the same as alpha raised to power 9, is the same as alpha raised to power 12. So, these are the conjugates. So, if you are exhausted 1, alpha raised to power 2, alpha raised to power 3, alpha raised to power 4, then you look at alpha raised to power 5. So, the minimal polynomial of alpha raised to power 5 should be the same as alpha raised to power 10, right, and so forth. So, very soon you will have those conjugates and you can multiply them out to constitute the minimal polynomial. Now, needless to say, here there only the highest power is x squared. So, only 2 of the elements have been multiplied out, right. So, once we have this table, we are ready to go back to our BCH codes. So, let us say we are interested in finding out a single error correcting code. Now, single error correcting means t is equal to 1, and let us fix n is equal to 15, because without fixing the n we cannot proceed. The two things you need to fix is n is equal to the block length and t is equal to the number of errors you need to correct, and then we will design our code. What is designing a code? Finding the g of x. That is what we mean by getting a BCH code. But we already have the algo for it. G of x is nothing but LCM of f1x, f2x. What are these? These are the minimal polynomials. When do you stop? f2t. But here our case t is equal to 1. So, we stop at f1, f2. So, f1x and f2x are to be multiplied from the previous table. So, if you go back to the previous table, we have the f1 and f2 right here, and now you understand the value of the LCM because they are identical here. So, we will only consider them only once, right. So, we take LCM of these two, and so any one of them, and the answer is g of x is nothing but x raised to the power 4 plus x plus 1. That happens to be my generator polynomial. Now, n minus k is 4 and n is already 15, consequently k must be 11. So, continuing that, we will get k equal to 11. So, we have certainly developed the first BCH code, the single error correcting 15,11 BCH code, which is a binary code. Okay. So, the design distance is 3, and you can verify using the generator polynomial that it is indeed the minimum distance is 3, leading to the fact that it can correct a 1 error code. Thus, the minimum distance is equal to the design distance. Now, we do not have to do much hard work if we have to graduate to the double error correcting code, BCH code. All we have to do is now increase the value of t is equal to 2, and now the generator polynomial is nothing but the LCM of f1 x, f2 x up to f2 t, but 2 t is 4. So, just the first 4 minimal polynomials and take the LCM. So, from the table we have written down this thing. Again, LCM comes handy because f1 x, f2 x and f4 x are identical, and so we will choose only one of them and multiply it with the second guy, and therefore, we are left with this following g of x. So, we have designed our second BCH code in a jiffy because we simply have the value of t is equal to 2. So, what do we conclude? The degree of g of x is n minus k, but here n minus k equals 8, consequently k is equal to 7. Therefore, k gets determined. Our BCH code is now 15,7, which is a double error correcting code. Okay. So, the design distance is 5, and you can also do the hard work and look at the either the parity check polynomial, or you can look at the generator polynomial, either which way, and find out what is the minimum distance. It is also equal to 5. Again, in this case, the design distance equals the minimum distance. Since this is a pretty mechanical process, we will go ahead and continue to the triple error correcting code. This also shows how versatile is designing a BCH code, because for example, a certain application requires us to put in a much stronger code. We can immediately go back and come up with a stronger triple error correcting BCH code. The GX is the same process, but this time the first 6 minimal polynomials need to be picked up. Once we do that and find out the LCM, we get the following. What is to be noted is the more number of polynomials we pick up, the higher is the degree of g of x. But higher degree means n minus k is larger, n minus k, but the n is fixed. So, k must go down. That means my redundancy is being added. So, g of x becomes a stronger polynomial, generator polynomial, at the cost of higher overheads. Again, k is equal to 5. So, we have BCH 15,5, which is a triple error correcting code. Again, one can check that it is indeed the minimum distance is 7, leading to number of errors to be.
It always happens that design minimum distance will be equal to that.
So, question is being asked whether the design distance is always equal to the real minimum distance. The answer is no, as we will see in the next slide. Let us go to 4 error correcting code, because it is so easy to go from one type of codes. Each one is an independent BCH code that we have come up with. So, we should appreciate the beauty with which we can immediately graduate to the larger and larger error correcting capability of BCH code. So, we are getting greedy. We have gone to t is equal to 4, and we quickly go to the first 8 minimal polynomials. So, you only do the hard work once in terms of creating that table, and once you have the table ready, we go all the way. And once we multiply it out and get the LCM, we get a very interesting g of x. It contains all the x raised to the power 14 plus x raised to the power 13 plus x raised to the power 12, so on and so forth up to x plus 1. Now, in this case the highest power is 14, n minus k equal to 14, consequently k is equal to 1, because this is a n is equal to 15 block length code. So, we have come up with a 15 comma, this is misprint, is a 15 comma 1, and this is nothing but a repetition code. So, this is a 15 comma 1 repetition code, and in this case the design distance is 9 because we wanted a 4 error correcting code, but if you go ahead and look at it carefully, this one has a minimum distance of 15. Consequently, it can correct much more than what we have designed for. This time we have over designed this 15 comma 1 code, right. So, actually it can correct up to 7 errors. That means our subsequent effort to go from 4 error correcting code to 5, 6 or 7, we will get the same answer, because we have run out of minimal polynomials, right. So, for t is equal to 5, 6 or 7, right, we have the potential, we will always end up getting that repetition code, because we have already multiplied out the minimal polynomials available to them. So, BCH code can correct larger number of errors than we have designed for. So, if we have to do better, we need to go to a Galois field which is higher. So far this 15 comma 1 repetition code can correct 4, 5, 6 or 7 errors. So, let us now extend this philosophy over a non-binary code. So, we are looking at a BCH code over GF4. Now, how do we do this? We are going to use a primitive polynomial pz is equal to z squared plus z plus 2 over GF4. So, since it is over GF4, it can have coefficients 0, 1, 2 and 3. 2 is already being used. So, 1 and 2 are being used here, and the extension field will be GF16. So, just to recollect, we will do our arithmetic over this GF4, which is the addition table and multiplication table given right here. Please note, GF4 does not follow modulo 4 arithmetic, because it is not a prime. So, we do the same exercise, but this time we have again elements of 16 GF16 constructed modulo pz z squared plus z plus 2. So, let us go back to our drawing board, and we have this time pz is equal to z squared plus z plus 2, and note it is over GF4. Now, if you see that the elements which are taken always modulo pz. So, if you have alpha raised to power 1, this is nothing but z, no problems. Alpha squared is nothing but z squared modulo pz. The moment you have modulo pz here, z square highest power, you divide it and you are left with z plus 2. And then you have alpha cubed, which is z cubed. Again you have to take modulo, because the degree of z is higher than z squared. So, you take modulo z squared and you get this time 3z plus 2. Now, in order to execute this operation, we have used the tables of GF4. The multiplication and addition tables of GF4 has been used to obtain this. Therefore, we get this, and the coefficients lie between 0, 1, 2 and 3, and so forth. You can continue up to alpha 15, which will give you 1, and then it will repeat again if you keep multiplying. So, all the powers of alpha can give you the 16 elements, but please note that the elements obtained in this table look different than the ones we obtained using GF2. So, GF16 can be constructed in both ways. We have constructed GF16 using two methods. Either you take GF2 and do prime power, or you have GF4. So, you can construct this. Of course, you have used here Pz is equal to Z4 plus Z plus 1, and here you have used Pz is equal to Z square plus Z plus 2. So, we have used different kind of primitive polynomials to construct GF16. But GF16 is unique, so the tables, the addition and multiplication tables formed either which way will show identical properties. But we go back to our slide, and now we look at the elements of GF16 as powers of alpha, and you have again the corresponding minimal polynomials. We do a quick observation. Alpha raised to the power 1 has this minimal polynomial, alpha squared same minimal polynomial, alpha 4 same, right, and so on and so forth. You look at alpha 8, you get the same minimal polynomial. So, consequently, you can now start looking at the error correcting capability of this non-binary BCH code. Please note, in the earlier example we had a binary case. Here the codes will be designed over GF4. So, we are again back to our square one. We would like to have a single error correcting code, t is equal to 1, very mechanical. Gx is LCM of f1 f2, but please note this time the minimal polynomials are changed. They take coefficients from GF4. Please note, minimal polynomials have coefficients 0, 1, 2 and 3. So, I multiply it out and I get g of x happens to be x4 plus x plus 1. You can multiply it out and use the tables of GF4. Again, degree is n minus k. I am looking at n is equal to 15, 15 minus 4 is 11. So, I have got a BCH 15, 11 code over GF4. We had a similar 15, 11 code over GF2 also, which is a single error correcting code. But the difference is that this takes 11 quaternary symbols and encodes it into 15 quaternary symbols. So, what is the big deal? Let us look at this example a little bit more carefully. So, this is a BCH 15, 11 code. This block BCH 15, 11 always takes in k is equal to 11 symbols and it encodes into 15 symbols. But please note, these symbols belong to GF4. So, consequently, you can actually use 22 bits to represent this, and here you have got 30 bits to represent the symbols, because remember GF4 can be represented using the 4 symbols 0, 1, 2 and 3, and they can be equivalently written as 0, 0, 0, 1, 1, 0, 1, 1. So, I can have 2 bits per symbol. So, what is the difference is it is a single symbol error correcting code. So, it corrects one symbol error, but one symbol contains 2 bits, implies 2 bits. So, suddenly bitwise we are correcting 2 bits, but if both the bits are in error, then also it can correct, because one symbol is a one symbol. So, it means that if I have a run or a burst error of 2 bits, I can correct it, because for me, if I am sending 22 bits and each of the 2 consecutive bits are paired together to form one symbol, then I am sending 11 symbols. If one of the symbol is wrong, I mean 2 bits can be wrong, then we can always correct 2 bits, but they can be consecutive 2 bits, they do not have to be random 2 bits. Consequently, it is actually a bit burst error correcting bit of 2 number 2 bits. So, if I extend this logic and if I say t is equal to 3, that means 3 symbols can be corrected, and so forth. But we will come to this later. Let us continue this example. So, we go back to our slides. So, we have for t is equal to 1, we have already a g of x over g of 4. Similarly, for t is equal to 2, we have got the same LCM methodology leading us to a g of x, which this time has coefficients over g of 4. That is all right, because our BCH code is non-binary. So, this is 15 comma 9. Why is this 9? Because n minus k is 6, n is 15, so k is 9. So, 15 comma 9 double error correcting code, but double error does not mean 2 bits, it is 2 symbols, and each symbol can be 2 bits. And mechanically we continue for t is equal to 3, we have yet another g of x resulting from the product of f1x, f2x up to f6x, because 2t, t is equal to 3, so it is f6, and therefore we have a triple error correcting BCH code over GF4. And we can continue doing this exercise, and we get for t is equal to 4, we have this following 4 error correcting BCH code, and for 5 we can take the same effort and get 5 error correcting codes. So, the point that we are making is it is extremely easy to get generator polynomials for BCH codes for the designed distances, extremely easy. Okay.
So, can we generalize that for t symbol error correction, the BCH code can correct 2 t burst errors? Is it always possible?
Okay. So, the question being asked is about the burst error correction. No. So, if we have to say burst error correction, we have to interpret it in a different way. The burst error correcting comes from its higher Galois field representation. Burst error comes because today you have gone to GF4 extension field GF16. This GF4 is represented using 2 bits. Therefore, it is a burst of 2. But suppose I had the luxury to go from GF16 to GF256. Here we have 4 bits. So, process is mechanical, but now I will be able to correct a burst of length 4. So, the strength or the burst error correcting capability comes because I am using a larger and larger Galois field to do so. Fine. So, please note that if this is GFQ, then I am looking at GFQ raised per m, where m is an integer. If you want to extend this further, can I have m equal to 1, and therefore, can we have, for example, GF256, an extension field is GF256. In that case, you are only focusing on burst error correction, and this is a special case because in BCH codes we have looked at different values of m. We just looked at m is equal to 2 and m is equal to 4, but what if m is equal to 1? GF2 to GF2 does not make sense, but GF256 to GF256 makes sense, because again I have the burst error correcting capability here. So, even if I have a single error correcting code over GF256, then the moment I say I can correct one symbol, single error correcting code, right, that means I can correct 8 bits, and I do not care whether all the 8 bits are in error, it is a symbol error. So, I will be immediately able to correct a burst of 8, which is significant. So, the special case when m is equal to 1 falls under the category of Reed-Solomon codes, which we will subsequently study, which is a subclass of BCH codes. But we go on and complete this exercise. So, we go back to our slides and we have the generator polynomials for t is equal to 4, t is equal to 5, and we can continue for t is equal to 6, wherein we suddenly hit x raised to the power 14. And if you have x raised to the power 14, then you know that this is a 15,1 6 error correcting code, but the moment it is n minus k is 1, it is nothing but a repetition code. So, obviously it can correct up to 7 errors even though you designed it. So, the design distance is more than what the minimum distance you are aimed for. So, point is the whole process can be mechanized, and you can find out for a given n and t a k and the coefficients of the generator polynomial. So, we can always make a table like this. So, here are some typical examples given. For example, for n is equal to 7, k is equal to 4, you can have a single error correcting code. For 15, these are all binary cases. So, this example we looked at 15, 11, 15,11 single error correcting code, double, triple. So, for example, the triple error correcting code, how do you interpret this polynomial is that n is equal to 15, we got this gx. Now, you write down all the coefficients. So, some of them are 0, some of them are 1, and that is exactly what you write. So, 1, 1, 1, 0, 1, 1, 0, 0, 1, 0, 1. So, all the coefficients are written up to this. So, that is how each one of them can be immediately written in terms of a polynomial. So, either I write the polynomials or polynomial coefficients. Now, very quickly we will go over the BCH error correction. Even though it forms a subclass of linear block codes and cyclic codes, we have already looked at the error correction of those. Let us quickly look over the BCH error correction in a more efficient manner. So, a lot of stuff we have already studied. We consider an error polynomial e of x given by the following: e n minus 1 x raised by n minus 1 up so and so forth, right. So, of which suppose new errors actually occur, where nu is less than t and t is the number of errors which we wish to correct. So, what are we considering? Suppose we have designed a triple error correcting code. Well, it should be able to correct also 2 errors or also 1 error. So, fewer than t errors should also be corrected. Up to t we should be able to correct. Now, either the errors are happening and where they are happening is also important. If we know what is the error and what is the error location, then we are home free. So, we would introduce this notion of the location and the magnitude of errors. So, the error polynomial is written as follows. So, binary codes either eik is 1 or 0, but in general it can be any value depending upon which Galois field we are working. So, let us start with the basics. We need to know for error corrections where the errors have occurred, that is the location, and what is the magnitude. For binary case it does not matter because it is either a 1 or a 0. So, if you found it to be 0, make it 1, so flip. But if it is a non-binary, say GF4, whether if it is a 1 and whether it should become a 0, 2 or 3, you have to figure out the magnitude of this error also. So, what do? We look at the syndrome syndrome can be obtained by evaluating the received polynomial at alpha. We did this theory in the last class, and that is why this 2t term came, why the gx is LCM of f1 x plus into f2 x into f3 x up to f2 tx. So, the same philosophy we write the syndrome polynomial as follows, and we then define the error magnitudes by yk and the error locations by xk. So, the syndrome can be written in the following way in terms of the error magnitudes and error locations. Now, we have 2t syndromes. So, we have got Sj equal to this evaluation at j is equal to 1, 2 up to 2t. And now, we have got this 2t sets of simultaneous equations, and we know that nu less than or equal to t errors have happened. So, we have nu unknown error locations x1, x2 up to x nu, and nu unknown error magnitudes y1, y2 to y nu, and our aim is to solve this x and y. Thus, we have a system of equations like this, and now some of the interesting algebraic manipulations and juggleries can be used to solve them efficiently. So, we define an error locator polynomial as follows. The zeros of this polynomials are the inverse error locations. Okay, this is how you define an error locator polynomial. Okay. So, if you see this lambda x is nothing but 1 minus x capital X1, the locations, and then we know the coefficients of the error locator polynomials can be obtained using the locations x1, x2 and x3. So, you do some manipulation in terms of the syndrome polynomial, and you can write it as follows. Finally, it can be represented in the matrix form in terms of the syndromes and the error locator polynomial coefficients. So, it can be shown that this matrix is non-singular if there are new errors. Okay. So, we should be able to solve this to correct for new errors, but we do not know, because we have designed it to correct t errors, and if less than t errors occur, what will happen. So, these are the steps that we do. We always start with the worst case. Suppose the maximum number of errors occur for which it was designed. So, you set nu is equal to t and compute the determinant of the matrix of syndromes M. Now, if nu is equal to t and t errors have occurred, then its determinant will be non-zero. If it is 0, it means that fewer than the number of errors for which you have designed have occurred. Suppose you have designed for 3 error corrections and only 2 errors have occurred, then the determinant will be 0. Then of course, you lower it to t minus 1 and so on and so forth until the determinant is non-zero. That will tell you how many errors have happened. Now, you have to find out where the errors have happened and what is the magnitude of the error. So, now it is nothing but solving this matrix as in terms of the set of equations in terms of the matrix. So, we solve the location polynomial, and if it is binary code, once you have found the locations of the error, you stop because it is either a 1 or a 0. If it is non-binary, we go back to the system of equations and find out the y1, y2 up to y nu, which are the magnitudes. Thus, we have been able to efficiently decode BCH codes using those nu cross nu matrix. So, people have done a lot of work on this, and you know, the entries in the diagonal perpendicular to the main diagonal are all identical. If you look at this thing, you see S2 S2, then S3 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 and so on and so forth, and diagonal S nu S nu S. So, this is a very peculiar structure, and this is called the Purse symmetry, and this structure was exploited by Berlekamp and Massey to solve the system of equations in a much simpler manner because of the symmetry. And another algorithm proposed by Forn is used to find out the magnitude of the errors. Consequently, this efficient technique is called the Berlekamp-Massey-Forn algorithm, and it is commonly used in the industry for solving the error locations and magnitude of BCH codes. So, finally, if we have to summarize, this is the flow chart. You have the input, you first find out the syndrome values, find the error polynomials, then find the error locations. If it is binary, stop. If it is non-binary, find the error magnitudes, then correct the errors, and you get the output. So, this is the flow chart of the BCH error correction capability. So, now we come to the end of today's talk. Let us summarize what we have done. We have looked at the generator polynomial for BCH codes, and then we look at how BCH codes can be used to correct multiple number of errors. And finally, we looked at some examples and figured out the Berlekamp-Massey-Forney algorithm for decoding of BCH codes efficiently. With that, we come to the end of this module.